Okay, today's notes are going to be introducing you to sections 1.4 and 1.5. We're looking at angle measure and angle relationships. Make sure you are following along in your guided notes or making your own notes. All right, there are a couple of different terms we're going to start with. The first one is ray. As you can see down here in facts, a ray is a part of a line. So when I model that, I'm going to have an endpoint and then just part of a line. It doesn't have an arrow on both ends, just on one end. When you name them, you will need points on them to name them. So let's make the endpoint A, and we'll make this point B, so it's just a point on the ray. When I name it, I'm going to use the symbol for ray, and then I'm going to name it AB. Make sure the first letter is actually the endpoint, so it kind of reads going from A to B, just like the picture. You cannot say ray BA because it doesn't start at B and go through A, so that one is not okay. We also have opposite rays, which if you have a point on a line, so let me get my line, let's say I have a point here, X, that point determines exactly two rays called opposite rays. So I have one ray going to the right and one ray going to the left. The one that goes to the right is called XY, and the ray that goes to the left is called ray XZ. These rays are opposite rays. If we take two rays and put them together, but not going opposite directions, so maybe like one going that way, the other one going out like this. I'm going to go ahead and get some points on them for you. Those are called angles. So when you have two rays together, notice that it says non-collinear because together they are not making a straight line, but they do have a common endpoint. When we name angles, the symbol for an angle looks like this. Sometimes we'll put a little arc through it, but an angle. And then to name them, I just want to use 3 points on the angle. One from each ray, and that middle point that they have in common, that end point. And I'm going to list them in the order that I see them going across the angle. That common endpoint, by the way, is called a vertex. So it's D in this case. Whatever that vertex is has to be the middle letter. So you could not call this angle FED. Not okay. The D has to be the middle letter. Looking back at the table we just filled in, I want you guys to try to work through these 3 examples on your own. So example 1, parts A, B, and C. And then I'll come back and look at them with you. So make sure you pause this. All right, so naming all angles that have a vertex, that have W as a vertex. So I'm looking at W here. So anywhere that this kind of maps it out. So right here, there's one angle. So that would be angle 1. And then if I go the other side of that, that's angle 2 right there. So angle 2. In between those is angle 3. If I trace out angle 1 and angle 3 together, those would be angle X, W, so let's see, X, W, Y. Similarly, I could put 2 and 3 together. So when I trace those out, let's see, V, W, Z. So again, I'm just tracing out the edges of those angles. And these two, you could have done the opposite way. You could have said Y, W, X. Those are the same angle. It's just different order. Do make sure though that anytime you use the letters, if you're talking about a vertex, it's W. W has to be in the middle. B says name the sides of angle 1. So looking at angle 1, one side is over here with the X and the W. Now, since the side is a ray, I want to make sure I use the symbol for a ray, and technically W is my endpoint. It's going out towards X. So when you're naming the sides of an angle, the vertex of the angle is what will come first when naming the ray. So for angle 1, it's WX, and then WZ. And again, that's ray, WZ. Another name for angle, WYZ. So WYZ. So I'm looking at this bottom angle down here. Well, one way to do it would just use the number inside of it, angle 4. Another way is I could do these same letters, but flip the order, making sure that the Y, stays in the middle. Okay, now we're going to look at classifying angles, and hopefully some of these sound familiar. A right angle, the measure of the angle equals 90 degrees. And sometimes, a lot of the times actually, when we're talking about the measure, let's just say for a minute, we're talking about an angle A. We would say the measure of angle A equals 90 degrees. And right angles make two perpendicular lines. They have that right angle right there. They don't necessarily go that direction. They could be down like this. But that little box means that it's a right angle and they are perpendicular. For acute angles, the measure is less than 90. So the measure of angle A would be, less than 90 degrees. So if straight up and down and then across is 90, it would be less than that. So something like this. And then for your obtuse angles, the measure is between 90 and 180 degrees. So the measure of angle A would be less than 180 and more than 90 degrees. So it's between 90 and 180. And you can see here, here's 90. It's more than that. And if you remember, straight across is 180 degrees, and we call that a straight angle. You may want to add that. Straight angle, the measure of the angle equals 180 degrees. And it's just like a line, where that's my angle straight across. Okay, go ahead and classify these angles as either right, acute, or obtuse. So pause this and then do that. For A, angle PMQ. So PMQ would be this angle right here. That is less than 90 because that would be 90. So we call that acute. Angle PMR. So that makes that whole thing right there from P over to R through M. That is perfect with a right angle there. Those are perpendicular. That is 90 degrees. And then QMS. It's a little hard to see, but you can turn on your paper, and if you drew a perpendicular box here, it would be like right like that. So QMS is actually open more than that. So that's called obtuse. Congruent angles are angles with the same measure. So angles with the same measure are called congruent. If you look at this picture over here, sometimes use those arcs to mark them as congruent. So since they're both 25 degrees, we would say that they are congruent. They are the same measure. And if I wanted to name those, I could name this left one as angle NMP. I would say it is congruent, which that's our symbol for congruent, to RMQ. In this figure, angle ABC is congruent to angle DBF. So ABC is congruent to DBF. Angle ABC, the measure of angle ABC is 6x plus 2. And the measure of angle DBF is 8x minus 14. I want to know the actual measures of those angles. So since they're congruent, that means they have the same measure. So I can actually set those equal to each other. Solve it like I would algebra, so I want to get all of my x's on the same side, so I'll subtract my 6x over. So on the left side I still have the 2. 8x minus 6x is 2x. My minus 14 is still there. Since I moved all of my x's to the right, I want to move my numbers to the left. So I'll add 14 to both sides. So now I have 16 equals 2x. Dividing by 2 gives me that 8 equals x, which is great, except for that I want to know the measures. So if you remember, the measure of angle ABC equals 6x plus 2. So I'm going to do 6 times 8 plus 2. 6 times 8 is 48, plus 2 is 50. Why don't you go ahead and do that on your own now for angle DBF? Make sure you've paused it. Since it was 8x minus 14, I'm going to put my 8 in there for the x, minus 14. 8 times 8 is 64, minus 14 equals 50. They are both 50 degrees, so my answer would be the measure of angle ABC equals 50 degrees, and the measure of angle DBF equals 50 degrees. Adjacent angles are angles that lie in the same plane, have a common vertex and a common side, but no common interior points. Okay, if you look at the example, A, B, and C are right next, that's right, angle A, B, and C is right next to angle CBD. They share that side of CB and they have the common endpoint of B. Same over here. These are non-examples because it says angle ABC, which is that first one, and angle ABD. While they both have that common AB, the common side, they both have the common vertex of B, the second one has C inside of it. So these need to be just right next to each other. And then over here, ABC and BCD, they don't have common vertexes, even though they do have a common side. Vertical angles are two non-adjacent angles formed by two intersecting lines. So when you draw two lines, basically the angles that are across from each other, like this, are considered vertical, and then these two angles down here would be vertical angles. Non-example would be like those two because those were not formed by making two lines. That's actually three lines that you drew, one straight across and those two right there. Your linear pair is a pair of adjacent angles whose non-common sides are opposite rays. So it's essentially two angles that together form a line. In the example, you can see how together these two angles, we'll call them angle 1 and angle 2, they are also labeled right here, make a line, whereas in the non-example, they do not make a line. Go ahead for example 3 and name an angle pair that satisfies each condition. For A, I went ahead and kind of traced them out. First off, that 115 is definitely obtuse, it's more than 90, and that would be angle VZX. It is vertical with this whole angle down here, so both of those together, which would be YZW. Two acute adjacent angles, so I'm looking for angles that are next to each other and adjacent, and there are several options for this. A great one is down here with the 50 and the 65 degrees, so go ahead and name those. The last angle relationships we're looking at are complementary and supplementary. Complementary angles add to 90 degrees, and supplementary, add to 180. Hopefully those are familiar.